This video introduces Gaussian quadrature as a method for numerical integration. Gaussian quadrature is an important tool for numerical integration in finite element analysis because every single element in a structure requires a stiffness matrix, and to get to that stiffness matrix you need to integrate over the volume of the element. So focusing on the isoparametric stiffness matrix, we know that it's equal to the integral over the volume of B transpose times D times B. But in terms of the isoparametric, we have the B's defined in terms of S and T, and the element in global coordinates in terms of X and Y. What we can do, though, is use the property of the Jacobian determinant, which is that it's equal to the ratio of the areas, global to local. So in infinitesimal areas, that just means that the determinant of the Jacobian is equal to dx dy divided by ds dt, or in other words, we can substitute dx dy for Jacobian times ds dt. So that's what we do here. That gives us an equation for the stiffness matrix, which is going to be the stiffness matrix in the global system directly, but we get to integrate over the local coordinate system, the natural coordinates of S and T. And the nice thing about that is, first of all, the B's and the J are all defined in terms of S and T, but secondarily, the limits for S and T both go from -1 to 1 because it's this 2 by 2 square element. This is the integral we now want to solve using numerical integration. Before we get into the integration itself, let's talk about a few properties of this integral. First off, the B matrices in here depend on the nodal positions. The B matrix we developed in a prior video. We used the shape functions times the nodal positions in order to give us a mapping from the natural to the global system. And in that process, we were able to calculate the B matrix. So every B matrix is distinct for each element in the global system because it depended on those element nodal positions. For a good element, a good bilinear quadrilateral element, or Q4, both B and B transpose will have linear terms of S and T. So when you multiply B and B transpose, you're going to get a quadratic expression. But poor quality elements, because the determinant of the Jacobian enters into B, so we're going to be dividing by that twice and then multiplying by it again, we're going to end up with ratios of polynomials. So a poor quality element will have a polynomial for the determinant of the Jacobian. So we're going to be dividing by that. This means that we're going to have an issue potentially doing the integration because a ratio of polynomials is much more complex to integrate than just a single polynomial. However, for good elements, the determinant of the Jacobian is constant. For lower quality, it's going to be a quadratic term. So our real question here is, what can we do to allow the FE code for every single element to go through this integral and evaluate it? It will be a different integral for every single one. What do? Well, we turn to numerical integration. This is what the background is, the reason that we want to do Gaussian quadrature. So what is Gaussian quadrature? Well, first off, quadrature is just another term for numerical integration. It is a way of approximating the integral, or the area under a curve of a function, with the sum of rectangular areas like what's shown here. Gaussian quadrature in particular is designed to be, unlike the Riemann sums, which are generic, designed to be a most efficient approach for polynomial integrands. So you evaluate the function fewer times to get the same level of accuracy. And remember that good quality quadrilateral elements have quadratic integrands, so they are polynomials. In Gaussian quadrature, what we do is we change the number and the width of the intervals in order to get the accuracy that we desire for a given polynomial. Also, the height of the rectangle is not evaluated right at the midpoint, such as is shown in the figure above. It's actually going to be evaluated at a specific location chosen to give us optimal results for polynomials. And that location is called the integration point for the interval. And finally, the choice of the interval width and that evaluation point is what gives us a very efficient, minimizing the number of evaluations, method of getting an accurate result for a polynomial. Let's see how this works in practice. Let's imagine, for instance, that we have a function, such as shown on the screen, that's a function of s, where s is going to vary from -1 to 1, and we want to find the integral of this function on that range. So this is what we're trying to solve for. What we do with Gaussian quadrature is that we approximate this as the sum of a series of rectangles where W represents the width of the rectangle and f of SI is the height of the rectangle at a specific location, SI. So if we want to do a single integration point, then what we're going to do is evaluate the function smack dab in the middle and multiply by the width of the rectangle, which is just going to be 2. So height of, or S1 is evaluated at 0, so f of 0, and then the width of the rectangle is 2. That gives us an exact result for any linear integrand. As you might expect, you evaluate at one point, it's going to average out negative on one side, positive on the other, or above and below. We will get an exact result. However, obviously for the function shown here, it's not a great approximation. Well, what if we want something more accurate? Well, we can go to 2 integration points. So we have the same function here, and again, we're going to approximate it as the sum of rectangles, but now we're going to apply 2 rectangles as shown here, and we're going to evaluate those rectangles not smack in the middle of the range, but at specific locations. In particular, when we go from -1 to 1, the first location is at -1 over the square root of 3, and the second is at +1 over the square root of 3. So when I evaluate at those locations, that's minus 0.577 and plus 0.577, then the width of each rectangle is going to be equal to 1, and that's what gives me the equation shown here where I'm evaluating the function at 2 locations, plus and minus 0.577. This gives me an exact result for up to a cubic integrand. So quadratic and cubic would both give exact results for 2 integration points over the range of -1 to 1. Taking it one step further, if you want to get even more accurate, how about 3 integration points? In other words, evaluating with 3 rectangles. Here's where we're going to see that we want to actually change the width of the rectangles. You can see here the middle rectangle ends up being extra emphasized. It's a wider rectangle. Again, this is for a polynomial. That's what you'd want to have, is the center section to be more important than the outer 2. And what we're going to do is evaluate the left-hand section, which has a width of 5/9. We're going to evaluate at a position, again, from the -1 to 1 range. Its first position is minus 0.774. And then the middle section is a wider width, so that's 8/9. And it's evaluated right where the S is equal to 0. And then the last piece is again back to 5/9, and it's evaluated at a positive 0.774. This gives me an exact result for up to a 5th degree polynomial integrand. So it's a pretty darn accurate result, especially if you've got polynomial integrands for just 3 evaluations of your function. Now you notice I keep talking about this evaluation of the function, and that's important because it takes computer time to evaluate the function. Remember, the function here is actually a big matrix that we're evaluating, and we're doing it on every single element. So if you have to evaluate that matrix 1 location, that's a lot less time than, say, 3 locations here. Well, it's a third of the time. Let's wrap up this video with a quick example of using Gaussian quadrature to evaluate a nodal force vector. In a prior video, I showed you how to find the force vector for the distributed force shown, the Ty here. And we ended up with an expression that looked like this, where we had shape function 1 and shape function 4, each evaluated at the position where s is equal to -1 and y is equal to 2. So here I'm actually evaluating with t as my variable, but again the range is from -1 to 1. So when I plug in the value for, or the expression for n1 and n4, we end up with an integral at node 1 in the y direction that looks like this. That's the integral that we now want to use Gaussian quadrature to evaluate. So first of all, let's go back to, if I evaluate that integral directly, because obviously I can, it's a simple polynomial, I get 83.3 pounds as my force. So if now I decide to approximate that with a single integration point, which is going to be exact up to a linear integrand, notice this is a quadratic integrand, so it will not be exact. So at 1-point integration means I take the full width of the integral from -1 to 1 in the t direction, so that's 2, and then I multiply it by the function evaluated in the middle of the range, so that's at location 0. So that gives me this expression when I plug in t equal to 0 inside the integrand, and it gives me a final total of 62.5 pounds. That's a 25% error by using a single point integration. Let's try the 2-point integration, which should be exact up to cubic, and since this is a quadratic function, it should give me the exact result. So again, here I'm evaluating it with two rectangles. Each rectangle has a width of 1, and I'm evaluating at -1 over the square root of 3 and +1 over the square root of 3, where t is my variable that is plus or minus 1 over the square root of t of 3. Plugging that into my expression with the integrand, I get 83.3 pounds. So I have no error present when I do the 2-point integration, and that's what I expect because this is just a quadratic function. So that's just a small example of using this. In the next video, I'll go through what we do for 2-dimensional elements, and then we'll take that to an example to find the stiffness matrix using both 1-point and 2-point integration on a 2D isoparametric element.